want to optimize something, yeah? Like if I wanted to optimize my profit, what am I looking for?
Fast profit.
Yeah, the biggest profit, yeah? If I'm wanting to minimize the number of detentions that students are having, what would I be looking for?
Trying to get the smallest.
The smallest number, right? So optimization is both mins and maxes, okay? And so basically it's going to be very similar to what we've been doing. It's just now we have context, or there's like applications in what we're doing. So on your sheet, a lot of what we're going to be doing is dealing with shapes. So there's a nice little review of what some of the different formulas are for area, perimeter, volume, and surface area. Most of y'all are pretty good about remembering them. The surface area one, sometimes we forget, as well as sometimes we don't remember the cylinder volume formula, but all of those are there for you. Okay. And then as well as are the steps that we're going to look at, because optimization problems aren't hard. Because again, it's really doing what we've been doing as far as taking the derivative, setting it equal to 0, all those things. But because there is a contextual problem now, or words, okay, we do have to analyze what it's asking for us a little bit more, and there are like steps. So that's usually the hardest part, is like figuring out what to do when. So you can just follow along kind of while I'm talking about these. So our first step is just to read the problem carefully. Some of us don't always read through the entire problem. With these types of problems, I would also suggest underlining or circling, like given information or important things that it's asking. And we'll look at some of what that looks like. So then the next step is to draw a picture. Sometimes we're going to be given diagrams or pictures, and that's great. Then I would still suggest like label anything that needs to be labeled on the diagram. But if you're not given a picture, especially when we're talking about geometric type shapes, it's really helpful to draw a picture. So then your handout calls it the objective function. I tend to call it the primary function. So we are finding the primary function. And you might circle or underline it. Basically, that is the function that is being minimized or maximized. So whatever the question or the problem is asking us to minimize or maximize, that's going to be our primary function. Because then the next thing, so if you notice in all of your like area, perimeter, volume, surface area, we have more than one on all, except for like squares and cubes, variables, yeah? So what will happen is, once I write my primary function, if that's like area, where I have length and width, again, we're going to be taking the derivative. We don't want to take the derivative of something that has two variables in it. So what we will need to find is a secondary equation, and that's going to help us to solve. Okay. They call it the constraint, but either way it's the same. Because then step 5, we're going to substitute basically whatever equation we found on step 4 back into step 3, so that way we only have one variable in our equation now. Because then our next step is to differentiate, which remember just means take the derivative. Next we're finding our critical values, so setting it equal to 0 and solving. Is finding our number line, so similar to what we've been doing, they say test the points, but we just draw out our number line to test those points. And then the last step is to find your answer. But it is important to make sure that you're reading what the question is asking for. Seems kind of straightforward. However, because we end up finding a lot of different dimensions or things like that, you just need to make sure you refer back to like what does my actual answer need to be in terms of. Alright. Ready to look at an example? So this one's on the bottom of your page. So you can also fill it out down there if you want. But it says a rectangular box with a square base and an open top is to be constructed using 1,200 square centimeters of material. Find the dimensions that maximize the volume of the box. So what do we want to do? What was our first step?
Read it carefully.
Read the problem carefully. So we're gonna highlight or underline a couple different things. So it's a rectangular box. Is there anything important about our rectangular box?
Square base.
Okay, it has a square base. What else?
Open top.
We don't have a lid. Okay, so that's going to be important here in a second. What do we also know?
1,200 square centimeters.
Okay, is how much material we have, and then what are we looking to maximize?
The volume of the box.
The volume. Yes, no, maybe. Alright, what's our next step?
Draw.
Draw a picture. I have a picture on mine. There's also like a little diagram on your sheet. Okay. But if you want to draw your own picture or just label that as well, it can be helpful. Alright, then what are we looking for?
The objective function.
Yeah, our primary or objective function. And remember that that's going to be the function or the equation of what we are trying to maximize. So what are we trying to maximize?
Volume.
Volume. So what is the volume of a rectangular prism?
Length times width times height.
Length times width times height.
There we go.
Oh,
Okay? Alright, okay with that. But do we know anything about our particular box?
It doesn't have a lid.
Hmm?
It doesn't have a lid.
It does.
The length and width are equal.
Yeah, they're just equal to each other. So instead of length and width, we can just write it as x squared. You can use whatever variable you want. I just tend to use x's. Yes, no, maybe. So here's where, okay, right now if we were to take the derivative of that, we would have to take the derivative of that like with two different variables, and that's not a fun time. Okay, so that's why we need a secondary equation or the constraint in order to help us to be able to simplify this so that we only have one variable. Okay. Now, what other information did it give us?
1,280 square centimeters.
Okay, is what?
The material.
Okay, so what would that represent?
Surface area.
Now, you are going to have to be a little bit careful here. Because can I just use my standard surface area equation?
No.
Why not?
You don't have a top.
We don't have a top. Also, our x's are the same, right? So we're also going to end up with something that's a little bit more condensed. So in this case, we can also just kind of think through it. So for each of the sides, okay, like going around, what is the area of those going to be? Yeah. What's our, what do you mean by base? Okay. Yes. Because base, if you say base, usually we're talking about the area of the entire base. So we don't really call it, like, you want to say like length, width, those sorts of things. But for us, what is our length? X. Okay, so we have x times h. And then how many of those do we have? No. Because those are just going to be the ones going around the side.
4.
Because we do not have a cube. My height is not also x. So we have xh. Okay. And what would be the area of our base?
X squared.
x squared. How many of those are we gonna have?
One.
One, because we do not have a top. Yes. Are y'all okay with that? So now our goal, like our next step, is to solve. We want to pick one of those variables to solve for so that way we can plug into our other equation. And it doesn't really matter as far as the problem goes which one we solve for, because we will need both of them. However, in this case, is one of those equations or one of those variables going to be easier to solve for? Yeah, which one? Oh, I would not solve for x. Right, because I have an x here and an x there, and my second x is being squared, so you would have to do some funky math, right? My h is pretty easy, right? Because I would just subtract an x squared and divide by a 4x. And that'll give us h. We'll see where we got that from. Like I said, the hardest part about these problems is that there's a lot of steps. You gotta do a lot of things. So do we all see where we got our volume equation and now where we have our height equation? Alright, because now our goal is to substitute what we got for our h here into our volume equation. Okay. And remember, our goal is to take the derivative of that. We want to take the derivative of that like how it looks right now. Does that look like much fun to take the derivative? No, we've been doing a product rule and a quotient rule, which is not much fun. But can we simplify that?
Yes.
Yeah. Because we have an x squared on top, but we also have an x on bottom, yes. So those will reduce. Then I can also distribute my x. Are you okay with that? And we can divide both of these by 4. So what is 1200 divided by 4? And I'm distributing it in x, so I'll have 300 x. Okay. On my second one, I don't have anything to divide by, so we're just gonna have a 1/4. And then also we're distributing our x, so we get an x cubed. Now, is that much nicer to take the derivative of? Yeah. So, can we take the derivative now?
Sure.
Yeah. What is the derivative of 300x?
300.
What is the derivative of 1/4 x cubed?
3/4 x squared.
Okay. And what is our goal once I take the derivative?
Determine the critical values.
Correct. Our critical points. So, how do I find critical points?
Say we go to 0.
Okay. Okay, how do we solve for that? Subtract 300, and then we would multiply by
3/4.
multiply by 4/3. Yeah, and negative, right? To get rid of the negative. So you would have 300 or negative 300 times a negative 4/3. So I have a 300 on top, 3 on bottom. How many times is 3 going to 300?
100.
100, and I have then times 4, so we get 400. So what does x equal? Which is
20.
or
Negative.
negative 20. Right, so we're taking the square root. We do have to have a plus or minus. Now, if x is a length, do both of those make sense? We can't have a negative length, so we do end up only choosing the positive one. But if this was like a non-contextual problem, you would have 2 critical points. One at negative 20 and one at positive 20. Yes, no, maybe. Alright, so then we do need to check ourselves. So we are looking at 20. And we're plugging into where?
Original.
so technically this stops at 0, right? Because we don't care about the negative stuff. So what is something that's in between 0 and 20? That's going to be easy to plug in. 1's pretty easy, right? If I plug in 1 into my derivative, I have 300 minus 3/4. Is that going to be positive or negative? It's positive. Yeah. Okay. That was something that's after 20 that's easy to plug in. 100, sure. If I square 100 and then multiply it by 3/4, am I still going to have something that's bigger than 300? Yeah. So overall we would get a negative, right? Which is good because if I'm going from positive to negative on our derivative, what does that mean my original function is doing? Going from
Up to down.
increasing to decreasing, which means that we have a
Maximum.
maximum, which is what we want, right? Because we wanted to maximize our volume. Now it does ask for dimensions. We have 2 of those, right? I have 20 by 20, yes? But I still need my height. Do we have anything that I could get my height from now?
First equation?
What do you mean by first?
The v equals, under the secondary equation,
Which ones?
the 1200 equals 4xh plus x squared.
We could. So we can use this one. However, we already have one that we've solved for h in. So I'm probably going to use the one where I solved for h, right? But yes, that secondary equation is what we're using. So we're just plugging in. So we have 1200 minus 20 squared, which is 400. So what is, see if y'all are better with your mental math skills. What is 1200 minus 400? 800. And then what do we have on bottom?
160.
80. 800 divided by 80 is
100.
10. Nope, y'all didn't fare much better. Y'all messed up in different ways, but it's okay. We're okay with the calculus and the x's, but you just ask us to plug in some, do some just normal arithmetic. Man, we struggle. So that would be our answer.
Should go back to that.
Because we just need to refer back to, so notice that it says find the dimensions, okay? So we do want to list out all 3 of what the dimensions are. Questions on that? Like I said, none of the steps in and of themselves are hard. What makes them a little bit more complicated is just that they're so long, right? And that there's so many steps, and you have to remember which one to do and what order to do them in. What questions do we have there? Ready to look at another one? So it says a rectangular page is to contain 24 square inches of front. The margins at the top and the bottom of the page are to be 1 and 1/2 inches, and the margins on the left and the right are to be 1 inch. What should the dimensions of the page be so that the least amount of paper is used? So what do we want to do first? Go back to your steps. What do your steps say to do first? Read it carefully. Alright. So I'm containing 24 square inches of print, so that's pretty important. We also have some margins, so that's some additional information of 1 and 1/2 and then 1. And then we are looking for the least amount of paper used. So we're trying to find the what this time? The minimum. Okay. Next up, what do we want to do? Draw a picture. What's our picture gonna look like?
A piece of paper.
Okay. Okay. Set it.
No, the margins.
What does that mean?
The box inside the box.
They're not. They're 2D, not 3D. but yeah, it's a rectangle inside of a rectangle. Yes? So that's gonna be my printed area. And what do we know about our margins?
The ones that on the top and bottom
Are?
and 1/2 inches,
Okay.
and on the sides they're 1 inch.
Okay. Do we know anything else? From the beginning.
No. Most of the 24
Okay. So what is 24 square inches?
The paper.
The whole paper?
rectangular page. No, the blue. The blue.
Ah, the blue rectangle in the middle, right? Because just the printed part is 24 square inches. What does 24 square inches represent then?
The area.
The area. So we know that the area here in the middle is 24. We're okay with that. Alright, so I'm gonna label, because I know that this is area for the middle, yeah? So I'm gonna label X and Y. Are we all okay with that? Just to give ourselves some variables to work with. You can also label them length and width. I just tend to not like L's because they end up looking like ones a lot, so I usually stay away from L's. But what are we trying to optimize this time?
The size of the fair paper. The whole thing.
Okay, I mean, yeah. Like, so we're looking for dimensions, yes, but that is not the, like, concept of what we're trying to minimize.
The size of the paper.
Okay, which geometrically would be what? Area. Okay, so we're trying to minimize the area of the whole paper. Yes? So that's going to be my primary equation because that's what we're trying to minimize. So I have A equals, am I still going to have X times Y here?
No.
What would I have? Remember, this is the area of the whole paper. This is the area of just the printed part. Yes? Are we okay with that? We okay? Is something wrong with it?
No. Because I was saying I was going to say that, but I couldn't do like the simple math. I had to figure out what
Ah,
the numbers
gotcha.
were.
Yes.
But it's 2 and 3.
It is 2 and 3. Yes. Okay. So this is our primary equation, but right now I have x's and y's. Do we want x's and y's? No. So we need to come up with a secondary equation. Do I have any other information that would lead us to have a secondary equation? What do we also know about x and y?
To the side lengths of the inner,
Cool. And what do we know about the inner?
the area,
Is what? So 24 has to equal
X times Y.
x times y. Yes? So we can use that as our secondary equation to solve for one of our variables. In this case, it does not matter which one you solve for. Which one do we want to solve for?
X.
Sure. So we get x equals over y. So then we're going to take that and we're going to substitute that in for our x over here. So we're looking better. Now we only have one variable. Can I simplify that any further? Yeah. What can we do? Yeah, multiply, but yes. Okay. So what is 24 divided by y times y? Just 24. What is 24 divided by y times 3?
72 over 1.
And then 2 times y?
2y.
And then 2 times 3.
That's 6.
Yeah. So then just combining our like terms. Now do we have a much nicer equation to take the derivative of? Yes?
Yes.
Okay. Now, what are we taking the derivative of?
The whole page.
Yeah, but like on the left, what does that A represent? yeah, so I'm taking the derivative of area, yes? Taking the derivative of area with respect to what variable?
One.
Y, yes? So, my equation, or my function in this case, is my A. The variable that is inside of it is my y's. Are we all with me? And the reason that I specify that is because even though I'm taking the derivative with y's in it, right, it is not implicit. Does that make sense? Okay, it's just a variable, and this is in terms of y, okay, so I'm just going to take it like I would if they were x's. Do we all see the difference between if I had y equals stuff, or if I have something with x's and y's, versus this just has y's in it? Okay, so what is our derivative of 72 divided by y?
Negative 72 over y squared.
Yes. Okay, what's our derivative of 2y?
2,
And what's our derivative of 30?
0.
So then what are we doing?
It says equal to 0.
Okay, we're finding our critical points. How are we going to solve for that?
Minus 2.
Okay, subtract 2 and,
Multiply by y squared.
okay. Then what do?
Multiply by negative 2 on both sides.
And we get,
36
so we get that y equals,
plus minus 6
which one of those do we care about?
plus.
No, a positive one. Okay, again, we're stopping at 0 because we don't want negative dimensions of our sheet of paper. So what's something that's in between 0 and 6 that we could plug in?
1.
Okay, negative 72 divided by 1 is going to be still negative 72, and then if I add 2, do I still have a negative number? What's something that's bigger than 6?
10.
Sure. If I square 10, we get,
100.
okay, and is negative 72 100ths bigger or smaller than 2?
Okay.
Smaller, right? Because it's less than 1, so it's going to be smaller than 2, so we would end up with a positive overall. Which makes sense, right? Because we should be going from decreasing
Negative
to increasing, because we want the minimum this time. Yes? No maybe. Questions? Okay. So is that my final answer? 6?
No.
No? What does it ask us for?
There is the attitude.
It doesn't actually ask us for the area of the paper. It asks us for the dimensions of the page, right? So that's the whole thing. Yes? Okay.
Yep.
So first off, what do we need to find? X, okay. But I can just use my X formula, yes? So we have 24 divided by 6 gives us 4. So our 4 by 6 are the answers? No. What do we still have to do with those? Add 2 and 3. So we're actually gonna get 6
By 9.
by 9 instead. Which is why I said it's important to refer back to what the question is actually asking you for. Questions on that? Yeah.
So if you put the, like this, I know the answer is 6 by 9, but if you put 54, like would they still be points?
I'm assuming you mean by they, you mean the AP test. You would probably not get, full points, no. Because you would not get points for your final answer. Because that's not what they asked for. They did not ask for the minimum amount of area. They asked for the dimensions that would cause the minimum amount of area. So you would probably get, like, if this, most free response questions are worth like 3 points. So you would get like probably your first 2 points from taking your derivative correctly and finding your critical points correctly, but you would not get the last point for the actual answer. Which is why I said it's really important to read back what they asked us for in the question. Other questions? Alright, I think we have time for one last one. It's our rubber ducky problem. What's the not Elmo, but the one from Sesame Street that has a rubber ducky? Doesn't one of them have a rubber ducky? Bert? Doesn't Bert have a rubber ducky?
I think it's just yellow.
Yeah, he's just a yellow bird.
No, that's Big Bird. No, but like
What
Bert
was
and
it?
Ernie,
Oh.
right? Bert has a rubber ducky.
It's been than that.
Come on, guys. Y'all have never seen Sesame Street?
It's
been a while.
It's been a minute.
Alright, well, alright, so this says a manufacturer determines that between 0 and 1,000 rubber duckies can be manufactured, and that the cost of producing X rubber duckies is C of X, while the revenue will be R of X. Find the profit function P of X and determine the production level that will maximize profit. Sounds good, right? So this one's actually going to be slightly different, okay? Because we're not dealing with a geometric shape this time, right? So does it make sense to draw a picture? Not really. Okay? But it does kind of break it down for us. So it asks us first to find the profit function, okay? So what is P of X going to be?
R of X minus C of X.
Do we agree?
Yeah.
Yeah. So my profit is going to be how much I bring in minus how much it costs to make the rubber duckies. Yes, no, maybe? So in other words, our P of X is 0.0, no, sorry, is that right? So it'll be negative 0.01 x squared. And then we have 23x minus 16x gives us,
7.
and then minus 200. Yes, no, maybe? Yeah, okay with that? Okay. And then how do I find the maximum of a function? Take the derivative. So what's our derivative there? You can use your calculator.
Negative 0.02 X. Plus 7.
Okay. What are we doing with that? That equals 0. And solving. Oops, too many zeros there. So what would we do to solve? Subtract 7 and divided by our 0.02. What does that equal? Do we agree?
Sure.
Where did we get 350 from?
Isn't that 150? So just times by 50.
Looks good to me. Yes, no, maybe? And then the only thing that we would have to check for, right, we only have one option, is to make sure that before 350, right, we want to look at our derivative. If I plug in 1, right, that's an easy number to plug in, what are we going to get? Into my derivative. Positive, yeah? If I take something that's bigger than that, yeah?
1,000.
Sure. What are we going to get?
Negative there.
Negative, okay. Which is good, right? Because we want to be going from positive to negative, okay? But that's not quite my answer. The last thing that we would have to do is
Plug it back
back into our P. Because it asks us for, no, sorry, it just says determine the production level. So it doesn't actually ask us for what it would be. So the 350 is our production level, is how many we would be producing. So that is my answer.